Okay, we're going to do an optimization problem here where we are looking at a window that's kind of a composite made up of a couple different shapes. So we have the rectangular part and then a semicircle on top. And it tells us that the perimeter of the window is 32 feet. And we are supposed to maximize the amount of area of the window. Okay, so when we do these optimization problems, we know we're doing an optimization problem because we're supposed to maximize or minimize something. So we're going to need some area formulas here. So this one's a little tricky because there's different kinds of shapes and you might tend to use different variables for them. You'd really like to simplify this and reduce the number of variables, right? But let me write down some area formulas that might be helpful here. So area of a rectangle is base times height or length times width or whatever you want to call those two dimensions. And then I have area of a circle that you should probably know this. We need a half circle. So area of a full circle is pi r squared. We just have a half circle here, so 1/2 times pi r squared. All right, so I have some choices here about how I label this diagram here, but because the area of the circle involves radius, I'm probably going to try to do the whole problem using radius as one of my dimensions here. So this is a half circle, which means that the distance from the center to the edge here is r. And then I can write the base of the rectangle also in terms of r. It's going to be all the way across here. So this distance all the way across here is going to be 2r. All right, I have a height of the rectangle, and maybe I can't really write that in terms of r. This is not necessarily a square, although the way I drew it here in the picture sort of looks like it's a square, but it doesn't tell us that, so that's just a height. All right, so just thinking about what's happening here, I've got a picture, I've labeled it, I've written down some relevant information and things I know about this problem. All right, and then the next thing I need is the objective function. That's the function that I want to maximize or minimize. All right, so what I want to maximize is area. So I need an area function here. So area of the rectangle would be 2r times h plus area of the half circle. I have too many variables here in order to do single variable calculus. So I'm going to have to figure out something where I can reduce the number of variables here. For the problems we've been working on, those usually come from a constraint or some kind of restriction. Right, and so they told us that the perimeter of the window has to be 32 feet, so that's the constraint or the restriction. So I'm going to use that constraint to help reduce the number of variables in my objective function that I actually want to take the derivative of. All right, so I'm going to have 32, and that's going to be the perimeter of this whole window. So perimeter is distance around the outside. So let's just kind of think about the sides here. I have 2r is the base of this window, so, and then I've got h and another side that's also h, so 2 of those. And then I have the distance around this half circle. So that's really circumference of a half circle. So circumference of an entire circle is 2 pi r, or half the circumference of a half circle would be half of 2 pi r, so just pi r. So this distance around here is pi r. Okay, so here's my constraint. The idea with the constraint is you want to use that to reduce the number of variables here. So I'm going to solve this constraint for either r or h and substitute it into the objective function. Technically, either way would work. One way is probably a lot easier than the other. So just pause and think for a minute about what would be easier. Probably would be easier in the objective function if I could substitute in for h. If I substitute something in for r, that's going to be squared, and it's going to make my derivative or algebra more complicated. So it's probably easier here if I could substitute in for h. And notice that in the constraint also, it's pretty easy to solve for h. All right, so the algebra steps you do to solve for h, you might choose to do different algebra steps or whatever. So I'm going to subtract 2r and subtract pi r, and then divide the whole thing through by 2 to isolate the h. All right, and the idea there is that I want to substitute that into my objective function so that I get an objective function that's just in terms of one variable. All right, so I'm going to rewrite my new objective function down here with that constraint substituted in. Okay, so probably we want to do a little simplifying here. We're going to take a derivative and set it equal to 0 in order to find critical points. So I would probably do some simplifying here. If I were going to do this, I might notice that these 2's cancel, and then maybe I would go ahead and distribute through that r in this parentheses here. I maybe would notice that I have some like terms here, some r squared terms, in fact pi r squared terms, and I could combine those terms. This one has a coefficient of -1 pi r squared, and this one has a coefficient of +1/2. So if I add -1 plus 1/2, I get -1/2 pi r squared. Maybe you choose to do that simplifying, or maybe not. I'll go ahead and do that. You also have another r squared term here, but because it doesn't involve a pi, it's a little harder to simplify that. So one thing that can be really frustrating on problems like this is to make a small little algebra mistake at this step, which then messes up everything else. So try to be very careful with your algebra, and hopefully I didn't make any mistakes, and hopefully you don't make any mistakes either. All right, so at that point I have my objective function just in terms of one variable. Another thing that you should do, even if it doesn't really ask you to do that, is to think about the feasible domain of that function. Certainly r should be bigger than 0. Otherwise I don't have a window here that makes any sense. There perhaps is a maximum r value that you could think about too. If h is 0, you could maybe think about what the maximum r value is as well, but for sure r should be greater than 0. So maybe that turns out to be relevant in solving the problem, or maybe not. All right, once you've got your objective function and used your constraint to reduce the number of variables in that, if necessary, not every problem has that complication, then you're ready to find your critical points. So you're going to take your derivative and set that equal to 0, or think about where that does not exist. So we'll have 32 minus 4r minus the 1/2 times the 2 will be 1 pi r. All right, so there's my derivative. It looks a little bit messy, but the algebra here is actually not too bad. I'm going to set that derivative equal to 0. And solve for r. All right, so I would probably add 4r and pi r to both sides and maybe factor the r out. So I have r times the quantity 4 plus pi equals 32, and then divide through by 4 plus pi. If you want a decimal approximation, you can get a decimal approximation. Probably do that at the end of the problem. I'm just going to leave this in an exact form for now. All right, so I have 32 over 4 plus pi for my r. That's my critical point. I need to test to make sure that that actually does give me a maximum area. So I can either use extreme value theorem. If I happen to have a closed and bounded interval that is part of my domain, I could use the extreme value theorem and just look at outputs of functions and compare those. I could use first derivative test and look at values both bigger and smaller, make a sign chart, and look at where the function's increasing and decreasing to determine whether this gives a local max or min. Or I'm going to use the second derivative test probably easy on this one. The second derivative is just some constants. And that's negative. And so the second derivative being negative tells me that the function is concave down. So the critical point that we have has to be a maximum. So this point really does give a local maximum for our area function here. All right, and then the only thing that's left here really is to answer the question. It asks for the dimensions of the window. All right, so I have an R value here. So that's the radius for the circular part at the top. So you should label this. Don't just give a number. Say that that's R or radius. And if you've got a picture that's labeled, it should be clear that that's radius. So R is 32 over 4 plus pi, and our units of length were feet. And then maybe, since we also have a rectangle, maybe we also want to give the width of the rectangle, which is 2R. So 64 over 4 plus pi feet. And again, you can get a decimal approximation if you'd like to for that. And then the other dimension that we would want here is the height. So going back through your work, if your work is organized, you should be able to figure out how to use H here to plug in your R value and get your H. I'm going to do a little bit of rearranging for that just to make it a little cleaner here and not have to write out too many steps. I'm going to notice that 32 divided by 2 is 16. And then if I think about factoring an R out of here, I would have minus 2 plus pi over 2 times my R value here. All right, and if you want to simplify that, 2 goes into 32 16 times. These don't cancel, but you could simplify that some more. That's in feet in exact form. And again, if you want decimal approximations, you can get those. Just type that into your calculator. But I'm going to just leave them in exact form. A lot of times on my written homework assignments, I will tell you to leave answers in exact form unless otherwise stated. My math lab, you just have to read the directions if it asks for exact form or if it asks for a decimal approximation. All right, there is a problem on your written homework this week that is a lot like this. So go and try that problem if you haven't already.